we have learnt that the potential satisfies the Poisson's equation which is Laplacian of the potential is equal to minus charge density at that point divided by epsilon 0, or a special case is Laplace's equation which tells me that del square V is 0 in the places where there is no charge. This has consequences, and as we said earlier that we had also said that these becomes the differential equations for the potential. If we want to use these to calculate potential, we should be able to show that these give unique answers given a boundary condition. As for the consequences, I will just mention one thing. If I take del square u v is equal to 0, this implies there is no minimum or maximum of potential at a given point, right? And therefore, at a given point, if the potential is going to a maximum through a maximum at one point, it will go through a minimum on the other side. Good way of visualizing it, look at this part of your hand. In this, if you come from the side of your fingers and thumb, you are hitting a minimum. But if you go from the palm to the other side, you are hitting a maximum. So there is no maximum or minimum here. This is known as the saddle point. And this is where del square of this quantity, whatever the height if I calculate, is going to be 0. And what it means is there is no equilibrium point for a charge in a charge free region. Let us understand that. If there is no minimum or maximum, that means the potential is going through a maximum on one side and a minimum from the other side. If I put a charge here, it may be stable in this direction from which it is hitting a minimum, but on the other side it will start moving away. And this is a consequence of del square V being 0. Mathematical way of seeing this is as follows. Suppose there is a point where there is a maximum. Then if I take a very small sphere around it, and calculate divergence of grad V over this surface, this is going to be equal to, by divergence theorem, divergence of this grad V over this volume. This is going to be, by divergence theorem, grad of V dot ds over the surface. Since this is a maximum, or the other way, if it is a minimum, then grad of V is going to have the same sign over the entire surface, right? So if the point is a maximum or minimum of V, then grad V has the same sign over the surface. And this implies integration grad V dot ds is not equal to 0. On the other hand, look at this. This is del square V dV, and this is 0. So I am hitting a contradiction. And if I am in a contradictory stage, that means my initial assumption that either I am at a maximum or a minimum is wrong. So there can be no maximum or minimum. Physical way of understanding this is as follows. In a charge free region, Gauss's law tells me that E dot ds is equal to 0. That means in a charge free region, if there is a point where some electric field lines are coming in, some have to move out, all right, and therefore a charge put here can never be in equilibrium, because whatever lines are coming in, they are also going out. So charge will tend to move in the direction where the field lines are going out. This is equivalent to saying del square V is 0, and all that is equivalent. This is known, by the way, as Earnshaw's theorem, that in a charge free region, a charge cannot have an equilibrium point. Now let us go to uniqueness of solution. Uniqueness of solution of Laplace's or Poisson's equation for a given boundary condition. What we mean by given boundary condition means that we have specified that on a given boundary, what is the potential? It is specified. So let us take a closed boundary. It could be at infinity, and we have given potential at the boundary. Let us call it V naught, and let there be some charge inside this boundary given by rho r prime. So you are given that del square V is equal to minus rho r, given at that r, over epsilon 0. Let us assume there are two solutions, V1 r and V2 r, both satisfying this equation and both satisfying the same boundary conditions, and let a function phi r be equal to V1 minus V2. Then phi r satisfies del square phi is equal to 0 and phi is equal to 0 on the boundary. Why? Because phi is the difference between the two potentials, but both satisfy the same boundary condition and both satisfy the same Poisson's equation. Let us now look at divergence of phi grad of phi, which you can easily show by taking components, is equal to grad phi square plus phi grad square phi. It is something similar to, just to facilitate it, d by dx of a function f, d by dx f is going to be equal to df by dx square plus f d2f by dx square. It is similar to that, and you can, by taking components, you can show that. But now I am going to use this to show the uniqueness. Let us integrate both sides. This is divergence of phi grad phi. So I am going to integrate this over the volume. This is going to be equal to grad phi mod square over the volume plus phi del square phi over the volume. However, we have seen that del square phi is 0, so this term drops out. On the left hand side, I am going to get, by divergence theorem, integration phi grad phi dot ds over the surface is equal to grad phi square dv. But we have already seen that phi is 0 on the surface, and therefore this term also drops out. As a consequence, what I see is 0 equals grad phi square dv. However, grad phi square is always positive. It's a square. So grad phi square dv is equal to 0 immediately tells you that grad phi is 0. gradient or the derivative of phi is 0, so phi is equal to constant. At most, V1 and V2 can differ by a constant, but since they are the same on the boundary, this constant better be 0. So this implies V1 equals V2. What that tells me is that given a charge distribution, the potential, the answer given by solving Poisson's equation is unique. There cannot be two different potentials satisfying the same Poisson's equation and same boundary conditions. And rho equals 0 is a special case, and therefore Laplace's equation, also given boundary conditions, gives me the same answer. So del square V equals rho over epsilon 0 has unique solution for a given boundary condition. Right? So let's see how we arrived at this. We arrived at this by looking at a divergence of the difference where phi is V1 minus V2, and this we used to get that grad phi must be 0. A related physical phenomena is that if I have a closed surface with no charge inside and V same throughout the boundary, then field inside is equal to 0. This is pretty much like if I have a metallic sphere we considered earlier, but now let me take a metallic any shape of a metal, and I give it some potential, that this entire surface becomes an equipotential, because metals, there cannot be any difference between two parts, otherwise charges will flow from one side to the other, and the field inside a metal is 0. So this is very similar to that if I create a equipotential, a closed volume whose surface all is at the same potential, then the field inside will be 0. Let us give that proof using divergence theorem. Now del square V inside is going to be 0 because there is no charge. Again, let's take divergence of V grad of V, which will be grad of V square plus V Laplacian of V. But since there is no charge inside, this fellow is 0. Let us now take volume integrals. Divergence of V grad V is equal to grad of V mod square d over the volume. The left hand side I can write as integral V grad V dotted with surface is equal to integral grad V square over the volume. Please do not confuse between this V and this V. Now if you look at V grad V over the surface, we are already saying that this surface has the same potential. Therefore, this V does not vary over the surface. I can write this as, I can take this V out, then it becomes integral grad of V dot ds. What is grad of V? This is V minus E dot ds. Since there is no charge inside, by Gauss's law, this term is 0. And therefore, left hand side vanishes, and I end up getting integral grad of V mod square dV is equal to 0. And this means grad V must be 0 inside. So if I take something with constant potential, surface, closed surface with constant potential over the surface, then field inside will be 0. As an example, you can do this experiment at home. You take a metallic tiffin box and put your mobile inside. If you call that mobile, the call will not go through because the field inside is 0, everything is shielded, the waves cannot penetrate that metallic closed surface. So, this is also used to make something called a Faraday's cage. You take a almost closed metallic surface, although it's made out of mesh, and put your instruments inside, and they are not disturbed by any electrical signals from outside, because that electrical, and no matter what you do outside, the field inside is going to be 0, because for a metallic mesh or metallic surface, the potential all throughout is constant.